Welcome to The Explainer. Today, we are unpacking the sheer, staggering logistics and complex engineering it's going to take to build a future Mars colonization fleet. We're not just talking about planting a flag and taking a few quick photos here. We are looking at the foundational architecture needed to move tens of thousands of humans across millions of miles of deep space. It literally forces us to tear up the rulebook on orbital mechanics, vehicle design, and, well, how we actually approach interplanetary travel as a whole. Okay, let's dive into this. How do you actually transport 50,000 people to the Martian surface? And maybe more importantly, how do you do it without waiting years for Earth and Mars to perfectly align in their orbits? To answer this, we're looking at a radical new framework for spacecraft deployment, one that throws out some of the most deeply entrenched rules of traditional spaceflight. To really understand this approach, we first need to look at what's called a straw man plan. Now, this is basically a theoretical framework designed to strip away the noise. We aren't here to argue over the color of the control panels or who gets the window seat, right? A straw man plan deliberately skips those secondary details so we can focus entirely on solving the huge, real-world problems of establishing a Martian colony. It gives us a solid starting point to iterate on, criticize, and eventually improve. Section 1. Scaling the transporter fleet. The backbone of this entire plan relies on an escalating, highly coordinated rollout of transporter ships. Now, what's really interesting here is the sheer escalation of scale over just a 12-year period. In year 0, we start with the Explorer class. It's a super lean operation, just 2 crew members and 2 colonists. But jump to year 4, and we introduce the shuttle, expanding capacity to 6 colonists. Fast forward to year 8, the Caravan ship comes online, jumping the colonist count to an incredible 100. And by year 12, the Ark arrives, capable of carrying a staggering 1,000 colonists at a time. It's an exponential curve in transportation capabilities that completely dwarfs early exploration concepts.
But here's the kicker. This progression isn't just about replacing old ships with shiny new ones. Let's see how this builds. This plan uses a really clever piggybacking concept. When the shuttle missions begin in Step 2, they don't fly alone. They fly right alongside the Explorer ships. By Step 3, the Caravan ship flies alongside both the shuttle and the Explorer. Every single new mission incorporates the legacy ships into a growing armada. So, by the Caravan era, you don't just have 100 colonists arriving, you actually have 108, all arriving as a unified fleet.
And that whole piggybacking concept, it culminates in the Ark transporter. Just imagine the massive, city-sized scale of these ships, carrying 1,000 colonists each. Because they form a convoy with the Explorer, Shuttle, and Caravan classes, 12 years after that initial landing, every single mission cycle will deliver over 1,100 colonists at a time. It totally transforms space travel from these solitary, lonely expeditions into massive, coordinated logistical supply chains moving through the solar system.
50,000. Just think about that number for a second. That's the population of a mid-sized earthly town, entirely relocated through the Earth Embassy. Even delivering 1,100 people at a time in these massive multi-ship convoys, it's still going to take years and years of non-stop flights to move this many human beings off-world. You simply cannot achieve a population transfer of this magnitude with traditional single-ship missions. You absolutely need this escalating fleet.
Section 2. The vital surface landers.
So, we know how to cross deep space, but we still got to get these folks down to the dirt. That's where single-stage-to-orbit, or SSTO, landers come into play. There is a stark contrast in the engineering here. You have Earth landers battling a punishing gravity well in a fiery descent versus the agile, low-gravity Mars landers. While both vehicles share the exact same unified mission and core design philosophy, getting things from orbit to the ground and back again, the vastly different physical environments demand fundamentally distinct engineering. You can't just use an Earth lander on Mars. The physics simply won't let you.
Section 3. Breaking the launch window.
Now this is where things get truly controversial. I mean, this is practically guaranteed to elicit hisses from the traditional spaceflight techies. So, the crucial point is this: 6 months. Under this plan, spacecraft arrive every 6 months, completely independent of orbital alignments. In fact, starting with the very first mission, the Explorer crew will remain in orbit for half a year just to wait for and assist the next arrival. This continuous 6-month arrival schedule is a massive paradigm shift that redefines literally everything we know about interplanetary travel schedules.
To really grasp how radical a 6-month schedule is, we have to remember the rigid constraints of traditional launch windows. We usually have to balance onboard fuel against the velocity of travel to ensure gravity capture. Basically, if you fly heavy and fast outside a window, you don't have the retro fuel to brake and you just drift past Mars entirely, a total nightmare scenario. Launch windows exist specifically to minimize this exact risk.
But there's a quote that perfectly captures this shift in thinking. In reality, though, there is no cosmic pane of glass preventing a launch to Mars at any time. Traditional restrictive launch windows make perfect sense when you're firing a capsule at an empty, barren planet. You got to carry all your fuel with you. But the equation completely flips when human infrastructure, fuel, and facilities are already waiting for you at the destination.
Section 4. Refueling and Rescue.
And this brings us to what is arguably the boldest engineering pivot of the entire plan. If we aren't relying on planetary alignments, how do we slow down these massive incoming convoys? Well, the answer is refueling speeding spacecraft directly as they approach Mars. And this brilliantly illustrates how establishing infrastructure on the ground completely changes the rules of orbital mechanics. Mars-based refueling leverages the people, the facilities, and most importantly, the locally synthesized fuel already stationed on Mars. Instead of dragging all the necessary braking fuel all the way from Earth, which, by the way, vastly reduces the amount of colonists and cargo you can bring, the incoming fleet is resupplied on approach by the Martian colony itself.
Let's walk through the 3 massive advantages here. First up, it ensures gravity capture by providing abundant power for the retro rockets, completely eliminating the risk of flying off into deep space. Second, because you don't have to worry about conserving fuel for the braking maneuver, you can fire your engines harder and allow for significantly faster travel times from Earth. And third, it creates a rudimentary rescue capability. Now let's be real for a second. Refueling a speeding spacecraft mid-void is an absolute engineering nightmare, but the benefits of shattering that launch window are simply too massive to ignore.
So, what does this all mean? We've seen how scaling a fleet, piggybacking massive convoys, and shattering the traditional launch window through Mars-based refueling entirely rewrites the playbook. Could this clever engineering be the controversial key that finally unlocks the solar system? Could challenging these deeply held paradigms be the exact thing that transforms a 50,000-person Mars colony from a distant dream into an absolute logistical reality? It certainly changes how we look at the night sky, doesn't it? Thank you so much for joining me on this explanator, and keep questioning what's possible.